You initiate a massive, mission-critical computation. The progress bar crawls, the fans spin up, and eventually the system grinds to a halt. When you hit this kind of processing wall, the standard instinct is to simply buy a faster processor. But for modern data demands, that solution no longer works. To understand why, we have to look at the baseline standard that has driven computer design for over 4 decades, the von Neumann architecture. This diagram shows the core of the von Neumann model. Memory stores data, and the CPU executes it. Notice the physical bottleneck between them. Because of this structure, only one instruction can be executed at any given moment. Over the next 6 minutes, we are going to abandon that sequential constraint. We will diagnose the physical limits of standard processors and then build a step-by-step blueprint for a parallel computing system designed to fracture massive workloads. Before architecting a new system, we must verify the problem we are solving actually exceeds the physical capabilities of a standard single CPU. This graphic illustrates the physical hardware walls we've hit. First, transmission speed through physical copper wire is strictly capped by the speed of light. Second is miniaturization. We have hit an atomic-level wall where transistors physically cannot be manufactured any smaller. With single processor physics permanently maxed out, our engineering strategy must shift. We can't increase the speed limit, so we build more lanes. That brings us to the foundational software mechanic of parallel computing, taking a continuous, monolithic problem and fracturing it. Looking at this flowchart, we can see the 3 specific steps required. First, we break apart the large problem block into discrete pieces. Next, we instruct, translating those pieces into isolated lines of code. Finally, we execute those instructions simultaneously across multiple CPUs. There is a strict condition for this to work. The fractured instructions must be completely independent. If one piece of code needs the answer from another piece of code before it can run, the system will stall. True parallelization requires heavy software design up front. If the mathematics of the problem itself cannot be divided, no amount of advanced hardware will speed up the process. Once the software instructions are fractured, we need to map them to the correct hardware. Multiple resources can mean very different things depending on the scale of your workload. This diagram outlines modern hardware tiers. The central micro tier is a single multi-core processor. Outward is the specialized tier, pairing that computer with GPUs. Finally, the macro tier links distinct computers over a network to combine processing power. Modern high-performance computing rarely relies on one superchip. It requires selecting the correct hybrid of these hardware tiers to match the specific demands of the fractured task. The hardware scale you choose directly dictates our next step, determining exactly how those processors will access the memory they need to run their calculations. This schematic compares 2 memory architectures. On the left, shared memory uses direct bus lines, so multiple CPUs access one common memory block. On the right, distributed memory means each processor accesses local memory, actively communicating over a network to share data. Memory architecture is the circulatory system of your entire setup. If the routing is inefficient, your expensive processors will spend most of their time sitting idle, waiting for data to arrive. This brings us to a dangerous assumption in parallel computing. It is natural to assume that if you buy 10 processors, your job will finish exactly 10 times faster. This seesaw diagram illustrates why that perfect one-to-one scaling never happens. Observed speedup is constantly weighed down by parallel overheads. These are unavoidable deductions, including the time it takes to start up tasks, the drag of operating system software, and data communication delays. But the heaviest drag on a parallel system is a mechanical requirement called synchronization. Looking at this chart, you can see the synchronization problem. Because task runtimes vary, tasks that finish early reach a synchronization point and are forced to wait. Bar 1 and bar 4 sit completely idle, burning clock time until slower tasks arrive. This graph plots performance against the number of processors. The dotted line shows perfect theoretical scalability, but because of synchronization and overhead, actual performance follows the solid curve underneath. The gap between them is a permanent physical and software reality. Achieving high performance is not about buying more hardware to force the line upward. It is about aggressively minimizing those delays to close the gap as tightly as possible. Here is the entire interconnected ecosystem we've built. We start with a standard desktop, branch out into dedicated GPU units for specialized tasks, and network outward to massive server clusters for the heaviest loads. To get to this point, we bypassed sequential bottlenecks, fractured our instructions into independent code, mapped them to a hybrid hardware tier, and routed to shared and distributed memory to keep data flowing. This mind map shows where these systems operate. This architecture handles real-world applications that single machines simply cannot process in a human lifetime, from running complex astrophysics simulations and characterizing the human genome, to powering web search engines and large-scale data mining. The next time you run a massive query or render a complex environment, consider the invisible, multi-layered networks dividing and conquering workloads behind your screen. Parallel computing allows us to outmaneuver the strict physical limits of our hardware. It is the definitive engineering strategy we use to maximize our most scarce commodity, time.